So right now I'm going to give you a short introduction, a brief introduction to the boundary element method. Boundary element method is, I think, not very popular right now, not especially commonly used. But for some class of problems, it can be really a smart method to write quick solvers and pretty easy solvers. And it's got a couple of advantages that you will see and maybe appreciate. Also, if some of you are interested in aerodynamics and aerodynamic aircraft simulations, then, well, not very popular right now, but in 70s and in 80s, the external aerodynamics has been calculated mainly with the use of panel methods. If you know the term panel methods, then panel methods are really just the boundary element method for the potential velocity field around an aircraft. Good, then. A brief introduction to the boundary element method. You can easily solve problems with potential fields with the boundary element method. What's the idea? If you are interested in solving such a differential problem, a Laplace equation, then, well, let me show you one observation and then we will draw some conclusions out of that. Let me do the following thing. Let's assume we don't have a prescribed domain, like our domain is everywhere, for instance. And let me write the Laplace operator in polar coordinates. This would be, I don't know it by heart, the Laplace operator in polar coordinates looks like that. Plus 1 divided by r squared d to f with respect to d theta squared. Well, and this is r, this is theta. We've got polar coordinates, and that's it. It's for 2D, obviously. In spherical coordinates, you would have more. Now, let me introduce harmonic functions. What are harmonic functions? Harmonic functions are basically functions that fulfill this equation everywhere. Harmonic functions basically are functions whose the sum of second derivatives with space is equal 0 everywhere. And there are pretty many such functions. Like in 3D, you can easily prove, and easily prove means just calculate the derivatives. You can easily prove that such function phi 1 divided by r satisfies the Laplace equation everywhere. For 2D, you can notice that phi equal natural logarithm of r satisfies this equation everywhere. Well, let's quickly check. Let's use the Laplace operator in polar coordinates. So what do we need to calculate? d phi with respect to dr is like 1 divided by r. Then d2 phi with respect to r squared is, well, minus 1 divided by r squared. So let's substitute. Let's see. Laplacian of phi capital Phi is what? Is -1 divided by r squared plus 1 divided by r times that one, 1 divided by r. Well, and obviously, such a function does give the derivative with respect to theta must vanish. Well, -1 divided by r squared plus 1 divided by r squared is 0 everywhere. Okay? So, well, like a nice observation is that we do have a class of functions that certainly satisfy the equation that we want to solve. So let's exploit this concept. And now the idea of the boundary element method is the following. Well, let's assume we've got some geometry, maybe with some hole inside. And we are interested in solving the Laplace problem everywhere inside. So what do we do with the boundary element method? First, we need to introduce the space discretization. Space discretization in this case means introducing the boundary elements. In the panel method for aerodynamics called panels. And that's it. Like the boundary element method means that you only need to generate elements for the boundary and you do not have anything for the domain. Now, what's the next idea is you need to associate such functions, like, for example, so that you get intuition to that. You can think of such a function as a source. Because if you draw the, so to say, streamlines that are associated with such a function, it means like you've got some point inside that is the source, and like it generates a flow of whatever. This might be heat flux. In the radially in all the directions, and like why does it satisfy the Laplace equation? Well, it does satisfy the Laplace equation because you would see that if you got this, if this source is located at point 0, this means that you've got extremely high intensity, extremely high flux here where the circumference is extremely small. And then it goes like that. It's, so to say, it's d phi with respect to dr. Yeah, it should do, it should represent the flux generated by such a source. Well, and it turns out that it drops with that rate that on each circumference the flux is conserved, so it does not introduce any additional sources. It does not introduce any sources. It conserves, well, heat or energy if you use this function to represent, for example, energy, temperature, or flow velocity or whatever, with one singularity. The singularity is exactly at the center of this function. So you don't want to have the center of the function inside of your domain, because it would mean that you introduce some infinite, you introduce source and potentially infinite density of the flux somewhere in your domain, and that's unphysical. So what the boundary element method assumes is, okay, we can either distribute these sources along the line. You can define a bit modified functions, or like one of the assumptions would be you can locate the source just a bit away from your panels. Okay? The same here. It needs to be outside the domain. So you've got source, which is associated with each boundary element. Now, the next thing is that you introduce so-called control points. And the control points, one of the simplest choices would be that they lie on the boundary. Well, then you need to say, okay, I will have some phi j. Let's assume that this is our jth panel. And let me have a look, because it's j or I. It doesn't matter now, but it will matter a bit later. Okay, I think j. What is it? It's like some scaling coefficient, a, j, meaning the strength of this source, times natural logarithm. Well, what is phi j at x, y? Okay, differently. R. Do you understand that? Like it's the magnitude of the vector. So we need to have these functions, these harmonic functions, we need to associate with a particular source point. So they need to have the singularity at my coordinates and need to span the harmonic function everywhere else.
So Rj is the coordinate of the point outside of the domain, yes?
Yeah. Or we can say it right as, let's say, R as like source, okay? So that we do not have problems to distinguish it from the location of the control point.
Oh, okay. So the phi j, and I assume that there will be as many phi j's as the elements.
Exactly.
So these are like global shape functions?
Like these are simply global harmonic functions.
Okay.
They certainly satisfy your equation everywhere.
Okay.
Okay? So we've got as many phi j's, as many boundary elements we've got. Obviously, because you've got an explicit formula for phi, this means that you can easily calculate the value of phi for whatever point you choose, well, anywhere, it doesn't even need to be inside of the domain, probably outside the domain, it doesn't make sense, but you can calculate it everywhere. And now, what's the idea? If you have functions that certainly satisfy your equation, and what you do is, let's assume we want to solve the problem with some Dirichlet boundary, saying that you've got some v, well, whatever, v equals 5 and maybe v equals 7 everywhere here, okay? Whatever, you've got Dirichlet boundary conditions. So what's the easiest choice? The easiest choice is, you need to observe that you got these scalar coefficients, unknown coefficients, that define the strength of the particular source. And obviously, this source that is located here will give some contribution to the, well, okay, I didn't say one thing. You define the whole solution, sorry, let me call it U, solution field as a function of all strengths times Uj at R. Okay? Then obviously this source gives some contribution to the value at this control point, etc. Each other source gives also contribution to that point, etc., etc. So you can probably already notice one of the properties of the boundary element method. What is it?
It will be full matrix.
It will not result in a sparse matrix. It will also always result in a dense full matrix, because in boundary element method you couple all boundary elements with all other elements. The nice property is that you don't need to introduce the domain discretization, you just have the boundary discretization, so you've got massively less elements. Well, okay, the simplest choice, what's the simplest choice? The simplest choice is to write the equations this way, that if you sum contributions from all the sources at some location I, let's say this one is xi, yi, then what it needs to give, it needs to give the Dirichlet value at this particular point. Now, see, we can generate, we generate equations by indexing I. So we generate equations saying that we need to fulfill the requirement of having the proper value at the boundaries, so at the control points. Well, and we do have unknowns that are indexed by j. So you arrive at the, we can write I index boundary points or control points. J is associated with source points. As we have said,
I have a question. Should we integrate it over each boundary element?
That's a very good question. First, let me write it this way. You will have phi j x I, etc. Then you've got all a j's here, and here the vector of all vi's. Okay, and as you said, the matrix will be dense, it will be full matrix, so you need to deal with that numerically. For simple problems, you can probably have equations with just maybe 100 equations, 100 unknowns, not more than a couple thousand. So you can probably deal with that somehow. Questions so far?
Can we use the boundary element method only to the problems that are like steady state, or can we use it somehow to the unsteady problems also?
We can also use to unsteady problems, but it needs to be reformulated. And some additional unsteady functions need to be introduced as far as I know. But to be honest, I don't know much about that. I brought 3 scientific papers about the unsteady boundary element method. Yeah.
What about different boundary conditions?
What? Like, for example, Neumann.
Or Robin?
Like with Neumann, actually no problem. Like what you need to do to implement Neumann, you probably already see what you need to do. So you need to calculate phi j with respect to the unit normal vector at location I. So you basically generate a different matrix if you've got somewhere not the Dirichlet boundary condition but the Neumann boundary condition. You need to replace. You need to require that in your matrix. I haven't been thinking about the Robin boundary condition, the third type, but I think with these 2 matrices, you must be able to construct. You must be able to construct that. Also, good question coming from you. Like this one is a very, very naive way of implementing the Dirichlet boundary condition. A bit smarter would be, yes, okay, let's count the contributions this way, that you do not require that the contribution from that source to this control point gives you exactly like the sum of all these values gives you this value, but maybe you would rather want to require that the integral of this element is 5. Well, you can define the least squares formulation, optimize it, and you will have an explicit formula that leads to a system of linear equations. What would you use for integration? Gaussian quadrature again. Okay. Then, well, a couple of nice things of the properties of the boundary element method. One of them is if you go to 3D, this means that you only need to discretize the boundaries of the surface. It's much easier to discretize the surface than to discretize the domain. One more thing is, maybe you define the control points somewhere. Is it a big problem if you want to split one of the elements this way? Having non-conformal mesh? No, exactly. Like that's a pretty nice feature. You can do it this way, and you can still work with that actually with no problems in the implementation and fulfilling the equations. This means that if you start with a dense mesh somewhere, you can probably build aggregates quickly, so to say, loosen the requirements for fulfilling somewhere on a dense mesh very, very accurately. So you can easily build some approximations to the correct, or to the more accurate solution. So both the splitting or aggregation is pretty much possible. One more thing, and it's probably the last one that I want to mention for boundary element method, is let's think for a while. What kind of data structures do you need, and what kind of geometry representation do you need? Let's assume, for instance, that we want to handle the solution of a Laplace equation on some geometry like that, meaning that we know this curve, we know we might have just some analytical representation of these 5 curves. And by analytical representation, I mean that you've got some explicit formula such that SI is defined as something that starts with the one-dimensional coordinate in some reference domain and transforms it to X and Y. Yeah? Then if you've got I think it's called natural parameterization, that if you've got natural parameterization, then you can easily use that. It's very, very easy to subdivide it into, let's say, 10 intervals. Then with the natural parameterization, you've got the guarantee that these points will be equal distributed along the curve. It's very, very easy to do it for each other of these 5 curves. So to say, we have just generated the mesh without any mesh generator, to be honest. What do you do next? Well, these curves certainly they do have some orientation, because otherwise you wouldn't know what is the inside, what's outside. So it's easy to generate locations of these source points and the control points, and just see this one, and probably the boundary values that you require as the Dirichlet boundary condition. It's everything that you need to know to solve the Laplace equation in such a domain. That's pretty nice. That's a pretty nice property to be kept in mind when you deal with Laplace problems, to be kept in mind if you want to write some initial solvers that might be dealing with really small linear systems of equations and solve the problem that doesn't need to be solved by finite volumes or finite elements. The disadvantage is that you come up with the full matrix, but maybe you can come up with a reasonably small full matrix. Or if you've got problems that you want to solve multiple times in the same geometry, then you can calculate the inverse of a reasonably small matrix. This can probably still be done like for 200 equations. This can be done, or you may run the LU decomposition to really very, very effectively solve the problems. Questions? Okay, we still have got the next hour to define the first assignment problem. Let me let me use a couple of more minutes before I go to the assignment to cover some numerical tricks and some other numerical topics that you should be aware of and investigate once you need them. No, they will be general. They will be general, mainly associated to what to do if your numerical problems do not want to converge. What techniques do you have in hand? Okay, so let's start with them. The first one is time stepping. I'm not going to give the whole lecture about numerical methods for solving ordinary differential equations. There's a lot to say, but let me remind that we very, very much like starting with the first order Euler method for time stepping. It's an easy choice for the implementation, but it's not a particularly good one. So I just want to give you one more idea. Instead of using the implicit Euler method, which looks like that, I strongly encourage you to move to the second order scheme with respect to time, which would be simply using the second order discretization of the time derivative. This one comes from nothing else if you do what we've been doing with the stencils. Like if you...
Shouldn't there be one
n minus 1?
Should be, sorry, n minus 1. If you write such a stencil and you want to calculate the first derivative at this point, you will come up with such a stencil. So what it changes, it requires you not only to remember the previous time step and calculate the new time step, but it requires you to store two historical solutions during the time stepping process, and you only make a minor modification to your left-hand side matrix to discretize the time derivative. Now, the second topic, an important one, so this one was time stepping. The other one is linearization. We already have discussed the linearization quite a bit when talking about the steady state and unsteady state Navier-Stokes equations. One of the techniques, basically the technique that you take as the convection velocity, you take the velocity field calculated in the previous iteration. That one is called the Picard iteration. Or Picard linearization. What's a different, very popular in numerical methods? What's a different numerical method that you know for linearizing nonlinear equations or systems of equations?
Newton
Yeah, exactly. It's the Newton or NewtonRaphson method. We don't use it very often in finite elements. It requires, well, just a moment spent on the sheet of paper with the equations, but it's not very difficult. And if it works, it should work really nice. For those of you who don't know the Newton method, the idea is the following. Let me give it to you quickly. The idea is that you have some nonlinear function f at x, and you want to find the solution to the problem f at x equals 0. Well, you don't know what this solution is. As in every numerical method, you start with some approximation to this solution. And what the Newton method assumes is the following. Well, it takes the Taylor expansion series, saying that f at x plus some change in x can be calculated by f at x plus h times the first derivative calculated at my current location, well, plus all the other terms. But we omit the higher order terms. So it's the approximation. And what the idea of the Newton method is, okay, I'm here, I know the value, I can calculate the derivative, and I want to, let's move by h such that after I move there, the result will be 0. Good? Then what it says, if you take this as your numerical procedure, then it results in h equals minus f at x. Let me write it this way, at xi. Then the new approximation is like that. Take it again, explicit calculation of the function value, explicit calculation of the gradient, iterate. If the Newton method converges, it converges rapidly, like 5 up to 10 iterations. It's got quadratic convergence rate. So if it converges extremely quickly. The problem is it can diverge. It's not very difficult to come up with the shape of functions that, well, probably if you've got something like that, you might, and maybe you start here, what you can get, probably you can go somewhere here. Okay, maybe in this way you would converge, but believe me, it's really not very difficult to find functions where you will diverge from your solution, and with each iteration you will be farther and farther from your correct solution. But it's certainly worth trying. The NewtonRaphson method is the idea that you do the same thing, but you do it for a vector function. So you've got the whole system of nonlinear equations written in the form like that. So what's done is then the vector valued function at my current vector location plus my vector, well, displacement is what? Is value at that one plus vector h times what? Yeah. But what is it? It's a matrix, yeah? Because you've got a vector valued function. So basically you go, say, 10 scalar functions, and you've got 10 scalar arguments. So you need to calculate derivative of each scalar function with respect to each variable. So it's like, say, 10 by 10 matrix. This one would be okay. It's nothing else than the Jacobi matrix. It's the Jacobi matrix, and what you need to do in this multi-dimensional case is you need to construct the Jacobi matrix. It's not a big deal. Like, you need to derive that, but it's not very, very difficult. You take the current value, you solve the linear system of equations. As a result, you get the displacement by which you should move. Then, again, you calculate the new x I plus 1 as my current position times the displacement that I have computed. This one is something that you probably know from courses on numerical methods. You can do exactly the same in finite elements and finite volumes. You just need to incorporate it into your discretization, but you come up with maybe it looks bad that you need to calculate the derivatives. Believe me, it's not very difficult to calculate the derivatives with respect to the scalar variables that that you want to solve for. So it's not very, very difficult. Questions to that? Okay, if no questions, then a very, very important observation regarding the linearization. You may very often have in CFD problems that incorporate some problematic sources. I mean problematic sources, I mean you may want to solve such a problem. Like maybe your source term is somehow associated and highly nonlinearly dependent on the function. You've got diffusion and you've got the source term. Like, what are the approaches to solve that? Find elements, find volumes, whatever. How can you solve it?
You can put it on the right-hand side as a source term, and you can put it also on the left-hand side.
Exactly. One of the ideas is, let's discretize it with whatever you want. You get the diffusion matrix, and you've got some source term. Okay, let's maybe start with zero source term and some boundary conditions. So you get the first update. Well, the problem is nonlinear, so it doesn't fulfill the nonlinear equations. But, well, you got already some values, so let's calculate the source term. With this new source term, let's solve the problem again. Then we've got some maybe better approximation. Let's plug it here again, and so on and so on. Nice. The problem is that if it's highly nonlinear, you're much more likely to diverge from your solution than to converge. Or if you want to converge, what can you try to do if your iterative process diverges and you want to make it convergent? Yeah, under relaxation is cure for everything, but not a very nice or effective cure. But it's one of the ways. But I would suspect that if you deal with some highly nonlinear chemical kinetics, maybe some evaporation processes that almost do not take place until certain temperature, but once they start taking place, then you go like a couple of degree range when everything evaporates. Then I can tell you, you will have under relaxation coefficients like 100 or even lower. You don't want to proceed this way.
Another approach is to take it implicitly and then linearize it with, for example, NewtonRaphson method.
For example, you've got a couple of choices. Like one of the ways to linearize that is writing, please don't laugh at that, it's not stupid, it's u to the power of 4 times u. Smart? Ingenious. Like it's already the linearization, because right now you can move it to the left-hand side. You will have something that comes, well, forgive me using actually some mathematical shortcuts. You will have something that comes from the discretization of the diffusion operator minus u to the power of 4 times u equals, well, it equals 0, but you've got some boundary conditions, so the solution will be fine. And here I mean that where you've got something that comes from the diffusion, and that is applied to u. You don't know u, so these are your unknowns. But this one is already something that you can use as a linearized coefficient. Like obviously you need to make some tricks. One trick would be, obviously it's not u, you need to have some approximation to u. And one of the tricks is take it from the previous iteration. But I assure you, such a linearization is already much more stable than calculating that. So if you can linearize, put it implicitly to the matrix, it will be far more stable. Whenever you can, please do linearize source terms. Well, but you might have still problems. Maybe it will not converge. What can you do then? No, your previous idea. Under relaxation, exactly. Just use the linearization, but also use u n plus 1 minus alpha u n minus 1. And you will be far better off already. What's the other possibility? NewtonRaphson. Sorry? More under relaxation. Yeah, NewtonRaphson. Just calculate the, take the function, discretize it, we find elements or whatever you want. You will have discretized source term. That's why I don't want to do it here, but maybe we will do it during one of the assignments. You will get an example where you will need to go through discretization and apply a NewtonRaphson scheme. Then you also come up with the linearization, but I think something that looks different, because you will not have 0 on the right-hand side. You will end up with probably the, I don't want to guess, but you will have something from the previous iteration on the right-hand side.
I can write it because I did it a lot of times.
Okay. Okay. You will be computing the new ones, and probably like something like 5 will appear here because you really need to calculate the derivative.
Yeah, and there will be also that 5 if4, like the derivative times the value from previous, if we want to have it not on the age like we have below, but on the already for variables.
So you mean what here?
No, at the right hand side you will have plus u to the power of 4 times n and times u n.
Okay, might be. Whatever. Like we will be not guessing what's the final formula for such a...
Before the un to the power of 5, there will be minus.
Here?
No. One term before. No, after 0. Between 0 and, yeah, here.
Okay. You've got the expert in NewtonRaphson math. Yeah. Let me erase that. But the idea is that, like, the naive linearization is one thing. The NewtonRaphson method will linearize the problem, but it will exploit the derivative, so you will end up with a different coefficient, probably a different coefficient. Well, certainly the different coefficient is responsible for having a different convergence rate. Typically, NewtonRaphson has got much higher convergence rate if it converges. Such naive linearization will have smaller, lower convergence rate, but it will have a larger convergence radius. Convergence radius is describes the area where you can start your iterative process and it will converge. The NewtonRaphson method usually needs to be pretty close to the correct solution and then it converges rapidly. And the last topic that I want just to mention are the limiters. Limiters, I mean, you do have some physical problems that you know that the solutions of these problems must be within certain limits. For example, chemical concentrations. If you go below 0, it doesn't make sense. Even if you go numerically below 0, it can produce extremely many problems. If your formula are highly nonlinear and you get some negative concentration and you calculate the rates of chemical kinetics, it doesn't sound like something that will make you happy, really. The other case would be maybe not that problematic, but not very physical. The other case is if you've got a diffusion problem, so for example, a heat conduction problem, and you start convecting the flow. Imagine maybe you've got some walls of temperature 20 degrees, you've got water 0 degrees, you start convecting it, you know that for sure, whatever happens, your temperature values must be between 0 and 20 degrees. Like there is no other option if you have no heat sources or something like that. Unfortunately, in the numerical schemes, you may get oscillations and wiggles, and then having overshoots or undershoots with 22 degrees. Not very nice, absolutely not physical. Maybe not always it causes problems, but in some cases it may cause problems. But especially things like, well, turbulent kinetic energy. If you go below 0, doesn't exist, like no option. The limiters then like one of the very, very coarse and very naive way of applying the limiters is, okay, if anything goes below 0 and it should not, then like you've got solve something if u below 0 then u equals 0. Or equals 1 to the power of -6, because maybe for some reason it is important for you to keep it not 0, but very, very close to 0. A very, very naive way. In some cases it works, because really you will find problems where getting just slightly negative values immediately causes giant problems for you. What's the main drawback of that? If it's any conserved quantity, it's not conserved anymore. So this limiter is really a very, very bad choice. I think there are much more elaborate flux limiters, meaning that you derive the, we've been showing, for example, in defined volume part of the course, we've been showing how you calculate the flux between two different cells. We have given something that depends on the locations of the centroids, maybe on the values in one and the other cell. Now, and then you use this flux calculation scheme. Now, you can derive the flux calculation scheme in such a way that you during the derivation, you require that the result at the new time step is not allowed to be beyond certain limits. And by doing so, you can derive a flux limiter that whatever you do will satisfy this requirement that the result after this iteration will not be beyond certain limits. I haven't got specific examples right now, but maybe for one of the assignments, we could think of a problem that requires limiters. And let this summarize our whole course on numerical methods. You have learned different discretization techniques. Like we've covered, first we've started with the differential models. We went through find difference method, through find volume method, through find element method. Very, very brief introduction to boundary element method. And these are all your discretization techniques that you can use. But finally, the discretization techniques only generate the system of equations. And this will be either linear or nonlinear system of equations. And then you need to solve these systems. And that's where you certainly need to keep in mind all the techniques for proper time stepping with higher order time derivatives if possible. Certainly linearization is something that you will be doing all the time when dealing with CFD problems or even custom applications. You will probably need linearization or a NewtonRaphson method when you deal with radiative heat transfer, like the source term in radiation is temperature to the power of 4. It's already strong enough. If you're dealing with chemical reactions, evaporation, and source terms coming from such phenomena, linearization, make the scheme implicit, which means take the source terms to the left-hand side, put it to the matrix, linearize, under-relax, maybe replaced by a NewtonRaphson method if you know that you're within the convergence radius of the NewtonRaphson method and you want to rapidly accelerate the convergence. And keep in mind that you might really need limiters because some unphysical solutions to just a few iterations may kick out your solution process to the space. Questions? That's all I know about numerical methods for engineering. Maybe I know a bit more, but But I think it has been already a very broad course. I did my best to cover many techniques within, I don't know, 18, 20 hours probably. I think we could do much more, like we could be probably discussing finite elements at least for 15 hours with a couple of projects. But I think this should be like a really good and informative, not only start for you. I hope that this is a course that gave you many information about what to be aware of and where to search for information if you run into problems, because you will run into problems. Thank you.